So in this video, we are going to see, exercise again 1.3, question number 8. Let's read the question. Find three different irrational numbers between the rational numbers 5 by 7 and 9 by 11. So between these two rational numbers, we have to find three different irrational numbers. Okay, so as we know that irrational numbers are, so this is our irrational numbers. Irrational numbers decimal expansion is non-terminating. Let me note it down. It's non-terminating and it's non-recurring. So we have to find three such irrational numbers which are non-terminating and non-recurring. Also, irrational numbers can only be represented in decimal form. There is no other way in which we can represent irrational numbers. So let's make that point as well. Okay, only decimal, they only have decimal representation. This is very important point. So if I have to put three rational numbers, if I have to find irrational numbers between these two numbers, I can only do that in decimal representation. Thus, we need to find decimal representation of these two numbers. These two numbers are in p by q format. Okay, they are in fractions. We need to convert these fractions into decimal representation. Once I know decimal representation of these two numbers, then I can find three numbers between these two numbers. Okay, so let's do that. So I'm going to just note down the step. So let me write here. Step number 1. Okay, find decimal representations. Find decimal representations of 5 by 7 and 9 by 11. That should be our step number 1. So let's do it. Now we know that these are rational numbers. So their decimal representation will either be a terminating or it will be non-terminating but recurring, one of these. So we'll find out by doing actual division. So let's start with the actual division. So 5 by 7 is like this, 5 by 7, so 0.50. So 7 sevens are 49. Okay, 1 is a remainder, then 0, 7 ones are 7, so 3 is a remainder, so 30, and then 7 fours are, which is 28, so 28, 2 is a remainder, 20, 7 twos are, which is 14, so 6 is a remainder, 60, then 7 eights are 56, 7 is a 56, correct, 4 is a remainder, and once again we have 40, then 7 6 are 42, so 7 fives are, let's zoom on, okay, so that is 35, and then 5 is a remainder, and then 50, and then again 7 sevens are 49. So as you can see here, 50 is here, and we have once again got 50. So this whole process is going to repeat. So this becomes our, this becomes our end, and from here all the digits are going to just repeat. 7 1 4 2 8 5, and then block 7 1 4 2 8 5, and then repeat. So this is going to go on infinitely. Thus, we have found out decimal representation of 5 by 7, which is equal to, okay, what I'm thinking is to get this down, just a minute. Let's pull this down. Yes. So that I can write the decimal representations. So decimal representation of 5 by 7 is 0.714285 and bar. Okay. So what we have got is a non-terminating. Let's make a note of that. So it's non-terminating, definitely, because it goes on infinitely. It's non-terminating but recurring. Okay, non-terminating plus recurring, which is a valid decimal representation of a rational number. It's non-terminating plus recurring. Now similarly, let's go and perform the division of 9 by 11 and see what comes its decimal representation. So where do I perform 9 by 11? Do I have space here? Yes, I have space here. So let's go with 9 by 11 here. I'm going to use a different color. Yes. So we have 9 here and we have 11 here, 9 by 11. So 9 ones are 9. That's going to give me 2. Then I'm going to put a decimal, so 20. Then 9 twos are 18. Oh, and then I got 2, and then once again 20. So then this goes on, 9 2s are 18, again 2, 20. So this will go on infinitely. So we know that 2 is going to keep on repeating. Quite straightforward and short. So 9 by 11 in decimal format is now going to be, okay, let's look at this. It's going to be 1.2 bar, because 2 is repeating again and again. So this is going to be 1.2 bar, because 2 is also going to repeat infinitely. So thus we have decimal representation of 5 by 7 and 9 by 11. Both these decimal representations are non-terminating. So that's what this bar indicates, and they are recurring. So these set of numbers will repeat infinitely, and this will also 2 will repeat infinitely. Now we have decimal representation of 5 by 7 and 9 by 11, these two numbers. Now all we have to do is we have to find three different irrational numbers between, which will be between these two numbers. And how will these decimal representations be? They will be non-terminating and non-recurring. Okay, so let's get them out. So what I'm going to do is I'm going to copy this, copy, let's bring them down here, paste. Yes, so these are my two numbers, and I have to find three numbers. Okay, I have to find three numbers which are between these two numbers. So what I'm going to do is I'm going to take this here. Yes, and these three numbers should be non-terminating and non-recurring. So it's quite straightforward. There is not much to think, or there is not much logic in this. Just take any number which is greater than this. So this is 0.7. So I'll start with 0.8. So one number will be 0.8, which will be definitely greater than this and less than this. And now I have to make it non-terminating. Let me note it down. I have to make all these numbers non-terminating plus non-recurring. Why so? Because it's an irrational number, non-recurring. So that will be our three irrational numbers. Okay, so 0.8, and then I can just go with 1, 2, 3, 4, 5, 6, 7, 8, 9, and 9, 8, 7, 6, 5, 4, 3, 2, 1, dot, dot, dot. Okay, so this is a number, note, this is a number which is between these two, because it is 0.8. And is it non-terminating? Yes, you can see it's non-terminating. Is it non-recurring? Yes, none of the digits are recurring or repeating in any special format. So thus this is our one answer. So similarly, very quickly we can go with another one. We can start with 0.9, and then we can start with 1.1. Okay, just you have to be careful that these numbers are going to be between these two. So greater than 0.7 and less than 1.2. That's the only thing you have to remember. Otherwise, all these things are, otherwise the digits that you write after this does not matter. So I'm just going to follow the same format what I did here. I'm just going to write here 1, 2, 3, 4, 5, 6, 7, 8, 9, and reverse 9, 8, 7, 6, 5, 4, 3, 2, 1, dot, dot, dot. This dot, dot, dot is very important, because our irrational numbers are non-terminating. Similarly, 1, 2, 3, 4, 5, 6, 7, 8, 9, and repeat 9, 8, 7, 6, 5, 4, 3, 2, 1, dot, dot, dot. Okay, so these three are our irrational numbers between these two rational numbers. Okay, and that becomes our answer for this question. Find three different irrational numbers between these two rational numbers. Okay. And now we see the last question from exercise 1.3, where we have to classify the following numbers as rational or irrational. Okay, so we all know that the difference between rational and irrational numbers. Let me just note it down here. Okay, so rational numbers, okay, they could be either, so their decimal representation could be either terminating. So I'm going to just write it. So the decimal representation could be terminating, okay, or it could be non-terminating. And if the decimal representation is non-terminating, then it should be recurring. So it should be non-terminating and recurring. Whereas when you think about irrational numbers, so let me just quickly write it down. So when you think about the decimal representation of irrational numbers, okay, it has to be non-terminating. So non-terminating, and it has to be non-recurring. So there cannot be any repetition of digits after the decimal point. Okay, so this is like the definition of rational numbers and irrational numbers and how their decimal representation will be represented. Now using this definition as our baseline, we can easily classify these numbers as rational or irrational. So let's start with the easy one. Let's look at this number 0.3796. It is a terminating number. It's terminated. There is nothing non-terminating. So very obviously this is our rational number. So I'm going to just write here rational number. Okay, so this is done. Simple. Let's go with the next another simple example. 7.478478. Okay, as you can see that there is a repetition of these digits 478, then 478, and dot dot dot. Okay, so first of all, it's a non-terminating. This dot 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 indicates it's a non-terminating. So non-terminating. And is it recurring or non-recurring? It's recurring because 478 is repeating, 478 is repeating. So since it's non-terminating and recurring, this becomes our rational number. So I'm going to classify, or I'm going to write it down here. This is our rational number. So fourth one is also done. Now let's focus on the fifth one. Fifth one, as you can see, it's non-terminating dot dot dot. So it's either recurring or non-recurring. Depending on these two, it will be either rational or irrational. Now let's see if it's recurring. Can you find some pattern which repeats after some time? No. You can say this is 10, then this is 100, then this is 1000, then this is 10,000, dot dot dot. So there is no way we can find a group of digits which repeats after the decimal point. So thus this number becomes, it's non-terminating, obviously it's non-terminating, but it is non-recurring. There is no recurring or there is no repetition of digits. So non-terminating and non-recurring, it has to be an irrational number. So let's labelize this as irrational number. So I'm going to write it irrational number. So fifth one is also done. Now we have these two numbers remaining 1 and 2. Now they are not very straightforward because we have given square root. Okay. So first we'll start with number 2. It's square root of 225. Now if you know the square root of 225, it's a perfect natural number and it is actually equal to 15. Square root of 225 is 15. And 15 is a natural number. It's a perfect number which can be represented in the form of p by q, which is basically 15 by 1. And since it can be represented in the form of in the form of p by q, this number is a valid rational number. Okay, this is because square root of 225 is perfect, whereas square root of 23 is not any perfect number. So we'll come to this later on. But as for square root of 225, we have a perfect square root which is 15, and thus 15 is a rational number. So I'm going to labelize it as a rational number. So second one is also done. This is a valid rational number. And now last but not the least is under root of 23. So how do we find whether the square root of 23 is a rational number or an irrational number? So for that we should actually perform the square root division to find the value of square root of 23. So if we actually perform the the square root of 23, we'll find out that it's a infinite non-terminating process, and the digits are non-recurring. They are not recurring. So in fact, just to write it down, the value of square root of 23 comes out to be 4.7958315233 and so on. Okay, so as you can see in this square root of 23, it's a non-terminating, so this is non-terminating, and it's non-recurring because there are no digits that repeat. Thus square root of 23 becomes an irrational number. How do we come to this number? We have to actually perform the square root of 23 by the division process, which I'm not doing in this video, but if you do it, you will get this as the answer. So I'm going to labelize square root of 23 as a irrational number. So this is also done, and this becomes our irrational number. So thus we have classified the given numbers into as a rational or irrational. There are two irrational numbers, the last and the first one, and these three, second, third and fourth, are perfect rational numbers.